this module, you will learn about capillary rise. Consider a capillary tube, that is, a hollow tube with a very narrow bore. The word capilla is Latin and means hair-like. When you dip this capillary tube in a liquid, the liquid rises or falls in the tube. This rise or fall of a liquid in a capillary tube is called capillary action or capillarity. The capillary action of a liquid is a consequence of the surface tension of the liquid and the angle of contact of the liquid with the surface of the tube. The extent of the rise or fall in the liquid in the tube also depends on the diameter of the pore and the density of the liquid. If the angle of contact of the liquid with the surface of the tube is an acute angle, there is a capillary rise. The rise of water in a glass capillary tube is an example of this. The angle of contact for the pair of materials, glass and water, is an acute angle. In the case of the pair of materials, a glass capillary tube in mercury, the angle of contact is an obtuse one, and hence there is a capillary fall. Consider a capillary tube of radius r dipped in a liquid. With surface tension S and density ρ. Let the angle of contact between the given liquid and the material of the tube be acute. Hence, as soon as the tube is dipped vertically into the liquid, we observe a rise in the liquid into the capillary tube. As the radius of the tube is very small, the surface of the liquid in the tube is nearly hemispherical. Thus, we find a hemispherical surface of the liquid in the tube, referred to as the concave meniscus. Here, A, B, C, D, E represent the hemispherical surface of the liquid. A, B, C, D, A is the circular periphery of the liquid which is in contact with the inner wall of the capillary tube. The height of the liquid in the capillary tube is considered from the surface of the liquid outside the capillary tube, which is taken as the plane of reference to the lower end of the concave meniscus. Consider the liquid column in the capillary tube to be in equilibrium. Then, the forces acting on the liquid column are the force by the surface of the tube on the surface ABCDE of the liquid. Let this be F1. The force due to the pressure of the air above the surface ABCDE. Let this be F2. The force due to the pressure of the liquid below point G, which is in the same plane as the liquid outside the capillary tube. Let this be F3. Let W be the weight of the liquid in the capillary tube. The surface ABCDE of the liquid in the capillary tube meets the wall of the tube along its circular periphery or radius r. Theta is the angle made by the tangent drawn to the surface of the liquid, with the surface of the tube from inside the tube at the point of contact, and hence is the angle of contact. Consider a small part dl of the periphery along which the liquid surface is in contact with the wall of the tube. The liquid surface across this small part pulls the surface of the tube by a force SdL tangentially. According to Newton's third law, there is an equal and opposite force acting on the liquid surface by the surface of the tube. The vertical component of this force is SdL cos theta and its horizontal component is SdL sin theta. The vertical component of the force pulls the liquid in the vertical direction. The total force exerted on the liquid surface by the tube's surface across the contact circle is F1 and is denoted by integral SdL cos theta. As S and cos theta are constants, we get F1 as S cos theta into integral dl. On further simplification, we get F1 equal to 2 pi r S cos theta. This force acts vertically upwards. The horizontal components of the force across different elements over the entire contact circle act in opposite directions, and hence they cancel each other, resulting in zero horizontal force. The force due to the pressure of air above the surface ABCDE, F2, is equal to P into pi r square, where P is the atmospheric pressure. The direction of this force is vertically downwards. The pressure at point G in the tube is also equal to atmospheric pressure, as the point lies in the same horizontal plane as the surface of the liquid outside the capillary tube. Therefore, the force due to the pressure of the liquid below point G, which is F3, is also equal to P into pi r square. But this acts vertically upwards. As the magnitudes of forces F2 and F3 are equal and their directions are opposite to each other, they get cancelled. Now, the weight of the liquid in the capillary tube is the product of its mass m and acceleration due to gravity g, and acts vertically downwards. The mass of the liquid is the product of its density ρ and volume v. The volume of the liquid in the capillary tube is the sum of the volume of the cylindrical portion of the liquid from point G to E and the volume of the liquid in the concave meniscus. The volume of the liquid in the cylindrical portion is pi r square h. The volume of the liquid in the concave meniscus is equal to the volume of the cylinder of height r and radius r minus the volume of the hemisphere of radius r, which is equal to 1/3 pi r cube. Thus, the volume of the liquid V is denoted by the sum of pi r square h and 1/3 pi r cube. Hence, the weight of the liquid in the capillary tube W is denoted by rho pi r square into h plus r by 3 into g. As the liquid is in equilibrium, the total downward force, which is the weight, is equal to the upward force, which is F1. Equating the two, and simplifying for height h, we get h equal to 2s cos theta by rho r g minus r by 3. If the radius of the capillary tube is much smaller than h, the term r by 3 can be neglected and the expression for capillary rise becomes h is equal to 2s cos theta by rho rg. If the angle of contact theta is much smaller and close to 0, as in the case of a glass-water interface, we take cos theta equal to 1. Then, the expression for capillary rise becomes h is equal to 2s by rho rg. From the expression, it is clear that the capillary rise of a liquid is inversely proportional to the radius of the pore. We find many examples and applications of capillarity in our daily lives. The root hairs of plants have fine pores in them and hence absorb water from the soil by capillary action. A sponge has fine pores in it and hence sucks in water from a surface through capillary action. You have now reached the end of this module. In this module, you learnt that a capillary tube is a hollow tube with a very narrow bore. The rise or fall of a liquid in a capillary tube is called capillary action or capillarity. If the angle of contact of the liquid with the surface of the tube is an acute angle, there is a capillary rise. If the angle of contact of the liquid with the surface of the tube is an obtuse angle, there is a capillary fall. The expression for capillary rise is h is equal to 2s by rho rg. Root hairs of plants absorb water from the soil by capillary action.